Okay, so there's an error on the screen which I need to correct, so before I go any further. And that error is right here when it says f of x4. So the error is that if we are taking the left value of the function, or the left endpoint of each subinterval and plugging that into the function, then our last value would be here at x3. So it's x0, x1, x2, and x3. So I had too many elements here in my sum. So let's correct that. So it's f of x0 times delta x plus f of x1 times delta x and f of x2 and then f of x3 times delta x. So that's this last rectangle right here. And so we would not have f of x4 in this left area. Okay, but if we wanted to, I don't know what happened there, but if we wanted to do a right area with the same figure, well, we would just shift over. I would have to kind of redraw my picture a bit, which I will do. Okay, so if we're going to use right areas, then we would take the right x value of each, right endpoint of each subinterval and plug that into the function. So we would start with x1 and kind of draw your interval sort of backwards, I guess. x2, maybe I should use a different color here. x3, and then x4 would appear in this one. Okay, and so now our sum would be f of x1 delta x, f of x2 delta x, f of x3 delta x, plus f of x4 delta x. And so we would start with x1 rather than x sub 0. Okay, and so that's a right approximation. Okay, so neither one of these is perfect. They're both approximations, and neither one is better than the other. And we could also choose other values within each subinterval. We could choose the midpoint of each subinterval halfway through. We could choose the maximum value in the subinterval or the minimum value of the function. There's all sorts of ways to do this, okay? But no matter what we do, one idea that we haven't mentioned yet is that in this particular picture, I've fixed the number of rectangles to be 4, right? And that was an arbitrary choice. But notice that if you increase the number of rectangles, so in other words, you partition the interval from A to B into a finer partition with smaller and smaller intervals, more of them, then you will get a better approximation to the area because there will just be less error. And you can see that just by drawing a picture. I need a blank slide here, but I don't have one at the moment, so let's just use this. If I'm going from A to B here, and I do a whole bunch of rectangles, okay, there's just less room, less error, okay? So the takeaway from that is that as the number of rectangles increases, the estimate gets bigger and bigger, or better and better, rather. Okay, so let me go back to this previous slide. I'm kind of out of room here, but what I wanted to say was as this number gets bigger, your area approximation becomes more and more accurate. And so what we're going to end up doing is taking something where we have a limit, and this number will be going to infinity. Okay, but we'll get to that later, shortly.